let's talk about how charges behave on conducting materials. So here I have a sphere, and it'll be hollow. So it's just a spherical shell. So there's no material towards the center. If we were to make contact with this sphere with another charged object, so charge up a rod, plastic rod, touch it to the sphere, charges will transfer to the neutral sphere, and then what they're going to do is they're going to spread out as far away from each other as they possibly can. So if I touch this sphere with a positively charged rod, the positive charges will move away along that outer surface in all directions, so we're only looking at that two-dimensionally. But they will move until they are in static equilibrium. Remember, static means not moving. If I were to place another positive charge, just a single one, they would then shift, move as far away as they can away from each other, and then become static, stop moving. So, in order for a charge to move, it has to be placed within an electric field, because for the movement to happen, there has to be a force. So since electric field is force per charge, you must put this charge in the vicinity of electric field, a net electric field, and then there would be a force that would accelerate it. When there is no change in the object's motion, we know from Newton's first law that there has to be balanced forces, so that the net force would have to equal 0. Well, if there's no force on the charge in the space that you put it, then the net electric field would also have to be 0. So when we have a conductor and the charges end up in that static state, that means that there is no net electric field in the conductor or within the center of the sphere. If the sphere were solid, and we did the same thing, we touched it with a positively charged rod, the charges would still push each other as far away as they possibly could, which would end up on the outer surface of the sphere. So that in the center, even though there's material there, there's metal there, there would be no charges that are sitting anywhere within that solid object. All of them would be separated to the outside. And it doesn't only happen with the sphere. If we had a long bar of conducting material, and it had some thickness here, and we touch this long bar or plane of metal that has a significant thickness, the charges would spread out to the outer surfaces, again leaving no charge within the space between the outer surfaces. This happens for all conducting materials. Doesn't matter the shape. If our conducting material had an irregular shape, the charges would still spread out over the surface. But in this case, where there's a lower radius of curvature, the charges would actually be more tightly packed. And again, those charges would spread apart until they were in static equilibrium, so that there was no net force on any charge, so it's not going to move, therefore having a net electric field over that surface, over the entire object, equal to 0. And just to drive this point home again, if we had a conducting sphere that had thickness to it, so that in this space it could be solid metal, and again, think about it three-dimensionally. In this center space, this is a cavity, so that's empty space. So think about it as a hollow, very thick, hollow sphere. If, again, we touch that conducting object with a positively charged rod, the charges would still spread apart only to its outer edge. There will be no charge within this empty cavity, and there will be no charge, net charge, within that space within the conductor. In the case where we have an insulator, so if we had an insulating sphere, that means that the charges will not flow through the material, and we could place the charges where we want them. So we can load up one side with a lot more charge, we can distribute it through the thickness of the sphere, and then they are stuck there, they cannot flow. If you have that type of distribution of charge, there is going to be an electric field in there. Now, what we're going to look at is symmetrical distributions throughout insulating spheres. So we won't have like one side that has a greater density than the other side. What we can have, though, is a variation of the amount as we go from the center outward. So we can end up with a very low density amount of charge along the outside, and as we move closer to the center, end up with a much higher density of charge. In the next video, we're going to start applying Gauss's law to conductors and insulators.